Hello, it's Valentine from Simplistic, and what we're going to take a look at out here is how to solve a problem where the problem is asking us for a pH of a 0.250 molar solution of sodium acetate. That's NaC2H3O2. All right, so basically when you have a solution of sodium acetate, you have to think that sodium acetate in solution splits into Na plus and C2H3O2 minus. Na plus is a spectator ion, okay? So it's not really going to do anything, okay? But what the counter ion, which is C2H3O2 minus, is going to do is this is going to create its own equilibria in solution. So let's go ahead and write out the equilibrium equation for this species. So we write C2H3O2 minus plus water, and that is going to ionize to form, it's going to pick up a hydrogen from the water, so it's going to form HC2H3O2 plus OH minus. Now, so once we have this, we can see that this species essentially created OH minus in solution, and whatever we're going to find is going to be the OH minus ion concentration, which is going to give us the POH, and from that we have to back into the pH. All right, so let's go ahead and use our ice-table logic out here. So initially we're given 0.250 molar, which is the same as this in solution, 0.250 molar. And then you have 0 and 0, and then the change is going to be minus x, and then you have x and x, and then at equilibrium you're going to have 0.250 minus x, and out here you're going to have x and x. Okay, so the next step is we're going to write K. Now since this is a base, so we're going to read the base ionization constant. Okay, so Kb is equal to C2H3O2 times concentration of OH minus over C2H3O2 minus. All right, so that is what it is. So before we plug in these values on the right hand side, we need to know what is Kb. Turns out we don't have Kb. Kb can be found from a table, but typically in tables you find Ka for the conjugate acid. Okay, so if you find Ka from the table, Ka for acetic acid, which is this species out here, is actually equal to 1.8 times 10 to the negative 5. Okay, that's the Ka. Now, there is a relationship to find Kb. So Ka times Kb is equal to Kw. And Kw is 1.0 times 10 to the negative 14. That is a constant. So if you know Ka or Kb, you can find the other one using this relationship. So let's go ahead and do that. So we are trying to find Kb. So Kb is going to be equal to Kw by Ka, which is 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. This is equal to 5.555 times 10 to the negative 10. All right, so now we know this value. Let's go ahead and plug all these x's in here. So that is equal to x squared over 0.250 minus x. At this point in time, let's go ahead and assume that this x is really small. That'll make it easy for us to solve. So we get x squared is equal to 1.39 times 10 to the negative 10, or x is equal to the square root of this number, which is 0.000117 molar. Okay, so if you compare this, if you take that and you divide it by the number it's subtracted from, you get I'll just write that out here. 0.0000117 divided by 0.250, you will get 0.000047, which is much less than 0.05. Therefore, this approximation is valid, so we will continue with this number. So this is the concentration of OH minus ions in solution. So let's write that down clearly out here. Concentration of OH minus ion is equal to 0.0000117 molar. So the POH is going to be negative log of this number, which is equal to 4.93. And so the pH is got to be equal to 14 minus POH. And that comes from this formula, pH plus POH is equal to 14. So that is equal to 14. Let's put two decimals out here. 14.00 minus 4.93, which is equal to 9.07. So that is the pH of this solution. I hope that made sense. Thank you for watching.